Welcome to the Geek Nighter podcast and part 2 of the episode. If you like it, please don't forget to hit the like button. Now, enjoy the episode. Thank you. As you said, there are multiple blocks to see, and is the data here, is the latest value here, and then sometime the reads might take a little longer because it has to like look for multiple blocks. And I was reading that bloom filters or data structures like that help a lot to reduce that those number of lookups. So what is your take on that? Like, how are bloom filters used typically in such
Yeah.
databases?
So yeah, exactly what you are saying is that people want performance, like everything is fast and high throughput, but most important, people want the predictability of performance. And that's something, for example, that I've seen in Oracle,
Yeah.
where there is no background cleanup to be done. People really have the predictability of performance. If a query takes 2 milliseconds today, it will probably take 2 milliseconds always.
Yeah.
And with this, this is the challenge. The data ingest, yeah, that's easy. You just append in a tree and then it is flushed. And if you have enough memory, you still have the memory while it is flushed. So that's fine. But
Yeah.
for the query, it needs to be improved. And for example, there are already some optimization in RocksDB. So basically, Yugabyte started its shard is an LSM tree based on RocksDB, but for SQL database, it needs more predictability for complex queries. And then some things were, and in RocksDB, you already have kind of indexing within the SSD files, and
Yeah.
there is also big use of even if the latency from SSD is low, you have big use also of the file system buffers. But yeah, Bloom filters are used to quickly discard the file that you don't need. An index usually indexes all values or maybe ranges.
Yeah.
The idea of Bloom filter is you have a structure that is much smaller and that will reduce what you have to read.
Yeah.
It doesn't mean that it will when it will tell you to read this file or this file from offset to offset,
Yeah.
maybe you will not find your data. You will have false positive, but at least it can tell you that no, in this file you will not find this data, so no need to read it.
Absolutely.
And yeah, that's a balance. Updating the Bloom filters in memory and using them to query, and also
Absolutely.
updating them when SSD files are merged.
Yeah.
Before distributed SQL databases, I've seen Bloom filters, for example, in Oracle. They are used for parallel queries because for big analytics, you usually scan a lot of data. But if you can avoid of scanning ranges of blocks, then always good.
Yeah, absolutely. That makes sense. And as you said, Bloom filters have some false positivity rate, but that is again tunable. It will take more memory, but you can reduce the false positive depending on the use case. And some of the databases also provide this configuration to you to tune these level of configuration. So
But that's a challenge because you have a LSM tree for each table or index, and even for each shard because it is sharded.
yeah.
And in practice, people will not tune a few parameters for each one.
Yeah.
So it must be either the best default that fit most of it,
Yes.
or automatic tuning behind.
Automatic
And that's
tuning.
the challenge because even if, as we said before, it is important to understand how the database works, people want to consume database as a service without thinking about all those different knobs to tune.
Absolutely.
And even with databases that I've seen before, I mean, people either use all defaults or set values without even knowing what it is, just because they have seen a blog post somewhere telling, oh, it was faster with this parameter, and they put
Yeah.
that. And that's also what's interesting in consulting. You go to customers and you see all strange setting with no meaning, and
Yeah.
then you realize that there is a popular blog post with this setting, but didn't fit the workload for that.
Yeah. Interesting. Again, the same problem without understanding the context, just implementing something and changing the configuration. It doesn't really work. I think you mentioned a little bit on the hardware side, like what has the modern hardware enabled us to, come up with new techniques to solve new problems. So you gave an example, I think, of mechanical disks. But what is the, what has the advent of, let's say, SSDs brought in the world of databases? How it has changed the way we look at databases?
Yeah, it has changed the way we look at it for performance point of view. It has changed the structure and
Hmm.
also brought some of the problems.
Yeah.
Basically, mechanical disk, you have latency when you read for random reads and writes. They are quite good if you read sequentially. So if you full scan a table, that's probably okay.
Yeah.
But random reads, you need to reduce them to the minimum. And that was one goal of Bitrees. You read a few blocks in the index structure, but most of them will be in cache,
Mm.
and you go to the table just only for one block. This has changed with SSD because when you read from it, you have kind of no latency if you compare. The latency is very low.
Yeah.
So you can do a lot more random reads without thinking about doing sequential scans.
Mm.
And then, in this sense, you see that it can be okay to have those LSM trees, even if you have to read some part of many files. It's not that important. And for
Mm.
example, in Yugabyte, we just don't support hard disk. We support only SSD because it doesn't make sense.
Yeah.
So that's one thing about reads. SSDs are very good for random reads. But when it comes to writes, then you still have this problem. The latency itself is not the same as the mechanical disk where you had to wait to a mechanical thing. But SSD update by page. They do not update a byte or not even a small block.
Yeah.
They update pages. And then if you have random writes, you have to do a lot of work. And updating is like copy on write file system. So it's taking another version of it.
Mm.
And this means that you must have garbage collection.
Yeah.
There is garbage collection at all levels. There is in the application, there is in those SSD files with compaction,
Yeah.
but there is also in the SSD files. So random reads are okay, but you want to avoid random writes
Mm.
because this is additional problem with the predictability of performance, where usually you will have low latency, but if there are some garbage collection to do before acknowledging your write, then it can take longer. So this is also where SSD files are a good solution because the random writes in a LSM tree goes into the first level in memory. This
Yeah.
is where it is sorted.
Yeah.
And then you have only flush
Mhm.
or merge. So you can really write in append to file.
Mm. Yeah. That makes
So
sense.
this also adapts to the structure, adapts to the storage. But that doesn't mean that people think that SSDs have solved all latency problem. That was true when having your own hardware and using NVMe, for example, to access SSDs. But when you go to the cloud, you bring back some problems because the storage is a network call, fast network, but then again, some latency.
Mm.
And that's something that people may not always understand, that, yeah, SSD is fast, but SSD, to be able to have the cloud elasticity, the cloud provider we'll have to put SSDs in as a different service, as a block storage service, and then maybe add more latency. Still have to think about that, think about the cache.
Yeah, interesting. Yeah, it makes sense. Talking about the algorithms that are implemented. So since we are distributing the data, there are multiple nodes, and there are things are happening over the network, and then failures can happen. What are the typical algorithms? Let's say talking about consensus or failure detection and all those. What are these algorithms that modern databases typically implement?
Yeah, that's something I really learned when starting looking at Yugabyte. So Yugabyte uses the Raft protocol. Other databases, distributed SQL databases, use Paxos. I don't know exactly the difference. What I've read is that Raft was better described and then easier to understand, and yeah. So that's one thing. But I never thought about those before, because even if monolithic databases add some replication, I've never seen them using those consensus protocol. It was kind of primary sending to a standby, but there was no need to be ACID for the whole configuration. So to be sure that you have atomicity, including the replication. Usually it was a standby, can be in sync, so you do not lose data if you have to fail over to it. But the standby didn't need to be fully consistent, and especially because in the standby you can only read and not write. When you go to distributed databases, you need this atomicity. So in NoSQL, you don't need it because you have eventual consistency. But so you don't really need this atomicity. But when you replicate, you need it. So even NoSQL databases need consensus when they replicate. You need to replicate to a quorum to be sure that if one part is down, you can have data in another one. So basically, what I understood about those consensus protocol is kind of you interact with it without thinking of the replication. So for example, for LSM3, you just append new values in a log way, and the algorithm behind will ensure that this append will be on multiple nodes, will ensure that you do not wait for all nodes, because that would be too much in terms of latency, but you wait for the quorum, and then you know that if a node is down, you can find the latest value in the quorum. So basically, in the Raft protocol, you have a leader and followers. So it looks like primary standby, except that here it's not one database that is a leader and with followers. It's a part of a table, a shard. So a few set of rows, a few index entries. They have a leader. And for example, in Yugabyte, every read and write go to the leader. So this is your single point of truth for a set of rows. For other rows, it may be elsewhere, so it's still distributed. But you read and write on the leader, and then you always see the latest value. But you want to be resilient if the leader is down. So when you write, it sends it to the followers and waits for the quorum, the majority of them. Typical configuration, one leader, two followers. When you read, you just read from the leader. When you write to the leader, but it will send to both of them and will acknowledge your write when one has acknowledged it. Which means that if the leader is down, at least one of the two followers has the latest version. And then they have to discuss together to see which one is the latest updated, and they will elect the new leader from that. So that's the idea. You add more latency on writes, but you don't have to wait for everyone. You wait for the quorum. And this is also where you have to think about the deployment. Waiting for writes on navigability zone is okay, on different region, then you have to think where you place the leader and where you place the follower. But basically, that's a level between SQL and those LSM trees. And I mentioned that Yugabyte implemented the LSM trees by starting with the RocksDB code, and I think the Raft protocol was implemented by starting on the Apache Kudu code base.
Okay.
But then again, with a lot of changes, optimization for the context of distributed databases.
Interesting. Yeah, that is very interesting. And maybe developers don't need to understand how Raft is implemented, but it's still good to know, some of the trade-offs that databases make there, right? Uh, so understanding the context again. So it depends on how deep you want to go. You can always go like deep, deep, and deep. There's no limit to that, but at least knowing what kind of algorithms are used when things go wrong, when there is consensus required, because it's all distributed.
And also, they really need to understand what is beyond read and writes. It's important for me, even if in the basic distributed SQL tuning workshop, I explain the basic of that, because people must understand that when they read from the leader. When they write to the leader and one of the followers. Of course, it depends on the deployment, but if they have a deployment where there is latency between those, they need to understand that single row updates, for example, may take time because of that, and it can be better to do bulk updates because you still wait for it, but you wait for a batch of it.
Absolutely. Yeah, that makes sense. So talking about the future, right? Because you have seen like a evolution of different types of databases, and you more recently are working on distributed SQL flavor of that. Uh, let's say, talking about for coming 5 years or 10 years down the line, what do you see in terms of like the changes or the new ideas that are coming up in the databases world?
As a big fan of SQL, I am very optimistic because there were a period where people were just saying no to SQL. that came with the no SQL thing. Like, we don't need to think about it. SQL is too complex. We just want a put get API. For example, MongoDB was really good at that, providing the most simple API for the developers.
Yeah.
You put a document or you get a document, and that was really good. But this apparent simplicity, then when people need to think about consistency, about race condition, they have a lot of code to do. If they take a little time to learn SQL, then they can realize that then they don't have to think about those race conditions. They don't have to think about consistency, and also they can change the structure. If you have a JSON document, you feel the developer may feel more freedom by defining the structure in his code than just having a database that is agnostic of it. But then when you have to evolve the structure, you need different code.
Yeah.
And that also can be a problem for legal reason. You may have to archive data and be able to read data that was updated 10 years ago.
Yeah.
If the database has a structure, you will still be able to query with SQL. If the structure is in the code, then you have to archive the code with the data. You will need to read those 10 years old data with the 10 years old structure. And maybe you fixed a bug on it because it is application.
Yeah.
And then do you read it with the bug at that time or with the new version? Makes things more complex in long term. So short term, easier to start. You pay it later, but there are still cases totally understandable that a new company, a startup, they must grow fast in short term. So makes total sense that they start with document key values,
Hmm.
and maybe later move to SQL, where you can also add more use cases.
Hmm.
You start with one use case. That's fast. You have the primary key, you access to a document. But then at some point, other departments in the company will need to query the data. With SQL, you can keep the structure and add new indexes. With NoSQL, usually people will stream data to another database dedicated for that. So those are the limits. And yeah, in the future of database, I'm really happy to see that with distributed SQL, we can have the scale out and resiliency that we need without giving up on the features. I'm convinced about the need for all SQL features, because
Hmm.
I've seen them arriving in OLTP, in data warehouses through the years, just because we needed them. So they will come. And that was also in my opinion, the main point with Yugabyte. So this distributed SQL started with Google Spanner.
Hmm.
They had a distributed engine, but very limited SQL at the beginning. They added later. And then Cockroach DB did the same, but also with more SQL features, but they are still adding. For example, today they don't have stored procedure. They will probably have some of them later. So they add features. And Yugabyte, probably also because they came a bit after, seeing this new trend of going again to SQL features. So the idea of Yugabyte was we will need all those features. So rather than building one after one,
Hmm.
just take Postgres and plug that on the distributed storage and transaction.
Yeah.
And then you have all SQL feature coming with Postgres. There is still a lot of work to optimize them, but at least all features are there.
Yeah. Yeah. Yeah.
And the future, I see that as SQL, of course, with things that have been learned through the NoSQL area. For example, we need documents. Relational model is really nice, but not for everything.
Hmm.
But today, even monolithic databases all can store JSON, and Postgres, Oracle, MySQL have also good optimization to store documents in the right way. So SQL databases, the SQL API, Postgres is very popular. There are so many forks of Postgres using the Postgres API,
Yeah.
and all kind of data, not only relational, also documents. Yeah.
Yeah, makes sense. Makes sense. And I also believe that SQL is here to stay since it's there since long time. It's well understood. A lot of people have good knowledge in SQL. It's easy to write SQL, and most of us write like plain simple SQL. They don't write like really complicated queries. So I also believe that distributed SQL is going to be huge in coming years, and I see a lot of work done there. So.
And there are also a lot of tools to generate
Hmm.
SQL. For example, I've seen a lot of DBAs complaining about Hibernate because
Hmm.
they see only the bad side. There are some ugly query generated by it,
Yeah.
but it also solves a lot of problems. So the developers can use frameworks to interact with the database. Doesn't mean that they have to ignore everything about how the database works,
Yeah.
but just makes their code simple for many things.
Absolutely. Makes sense. Great. So this episode will give like a good insight into like different things that databases implement. But what if I have to know more? What are some resources that you would recommend to people? Maybe books, some videos, some courses, just for folks who are more interested into going a little more deep into databases.
Yeah, I would say first try it, because one thing we didn't say about the future of databases, the future is open source.
Hmm.
What we have seen with when I started, Unix was for enterprises and Linux was for your laptop.
Yeah.
And people were like, no, for enterprises, we need something like Unix's, Solaris, HPU, EXAX. But then it all came to Linux and open source. And I think we also see the same with databases. Commercial databases will stay, especially for things that have been built on DB2 Oracle. Many of them will just stay as is, but those who modernize their IT will go to open source. And that's something also easier to learn, because it's easy to start a Docker container on your laptop and play with it and look at it. Of course, there are some good resources. I can send it to you if you want to put it in links in
Yeah, definitely.
in the publication, because I don't want to be bad on the names of the authors or things, but there are really good books about distributed database, about those protocols, for people who want to go into the detail. But I would really start that it's easy. It's complex technology, but it's easy to start. And even to test resilience, you can start 3 Docker containers on your laptop and just pause one and see what happens with your application. Does it continue? Does it wait 3 seconds and then continue? So play with it. And also, I'm a big fan of any knowledge sharing, and what you are doing with this podcast is really good. But also going to conferences. Talking with other people. For example, I mentioned that I was very not a big fan of NoSQL. At the beginning, I was really like, what's this? There is no reason for that. But when you discuss with developers, for example, I can really also understand why they like MongoDB, why they like DynamoDB. So it's also good to meet people having different concerns, different use cases, different companies.
Awesome. Yeah, that's really helpful tip. Learning by doing and playing around with technologies, I think the best way and quickest way to get started. And then if you wanted to go deep into the concepts, and of course you can refer the resources for viewers. I'll take those resources from Frank and attach them in the description. So please take a look after you watch this video. And also I've created some of the videos on all the other databases. So if you wanted to learn more on Cassandra, on Yugabyte DB, how migrations work in Yugabyte, or Cockroach DB internals, please check out the other episodes on this channel. But after you watch this episode, so thank you, Frank, for joining and sharing all the insights, sharing your learnings and experiences with us. I'm sure people are going to get a lot of value from this episode.
Thank you very much, and thank you for what you are doing. Sharing knowledge in this way is really nice. Yeah.
Awesome. Thank you.